I am going to talk about extrinsic semiconductor material. I've already talked about intrinsic material, which is pure, and I have talked about doping and how it's done, and now I'm going to talk about what extrinsic semiconductors kind of do a little bit. So extrinsic semiconductors, and all this you should already kind of know, because this is all, we've talked about this before, that when we dope extrinsic semiconductor, basically they're either doped with donors that provide extra electrons or acceptors that accept extra electrons, so they provide holes. So anytime you see anything with a donor, you know that's going to be an electron. Anytime you see anything with an acceptor, that's going to be a hole. So we get N-type or P-type semiconductor material, which is basically the only two types that we will have in here, which you can do a lot with just those two things. When we add impurities, it changes the Fermi energy level, which we've also kind of alluded to, that where it lies actually is a direct relationship with how the material is doped. So when you have N-type material, the Fermi level is closer to the conduction band, which means the energy is closer to the conduction band, which means because you have more electrons than you do holes. If you have more holes, then the Fermi level is closer to the valence band. And that's what happens in P-type material. So remember, oh gosh, this seems like ages ago to me, but probably just last week. We had kind of this graph that we put together, the density of states function and the Fermi probability function, the Fermi-Dirac function, and we made this kind of interesting graphic, and it showed equal numbers of electrons and holes. And this is what intrinsic material looks like. It just has a certain amount of electrons, certain amount of holes. They're created in pairs, and they're equal. So the same thing, if we take that and apply it to N-type material, what happens is the bubble that has N material or electrons gets bigger, and the ones with holes get smaller. So what ends up happening because of that, you'll notice that in this picture, the Fermi equation, which is the green dashed line, crosses the intrinsic Fermi line, which is the black dashed line, right in the middle of the line. And then when we go to N material, right now it's not crossing, it kind of shifts to the right, but the actual Fermi level is at that point when at the center of the line. So the Fermi energy level actually crosses the center of the Fermi-Dirac function, and that's reflecting the fact that there are more electrons than holes. When we have N-type material, we can figure out the amount of electrons a number of ways, and we're going to get into some other ways of doing it. Well, today or another day. I don't remember. Maybe not today, because I really don't remember. I just sort of go with what's in front of me and hope that I say the right thing. Anyway, in N-type material, what we end up with is we can calculate the number of electrons if we know the intrinsic value and the difference between the Fermi energy and the intrinsic Fermi energy. So this little space right here, if we know how far above the intrinsic that the Fermi energy is, we can figure out exactly how many electrons there are. And there are going to be more electrons than holes, and the Fermi energy is going to be greater than the intrinsic Fermi energy. So all of those things you can get from that graph without me actually telling you that. P-type material is going to be exactly the same. Oh, I forgot to say something. Electrons are the majority carrier, and holes are the minority carrier, because we still have holes. Even though we have more electrons than holes, we still have holes. So there will be, when we get to the point where we're talking about actual devices, there will always be electrons and holes involved in charge carrying. It's just that the one that there are more of is the majority carrier, the one that there's less of is the minority carrier, and depending on where you are in the semiconductor device, one or the other could be responsible for the charge flow that you're actually experiencing, depending on the device. Some devices are majority charge carrier devices, and some are minority charge carrier devices. They just kind of work that way. So anyway, now when we go to p-type material, you'll notice the area where the hole concentration is larger. So now the Fermi energy is going to have to shift downwards so that it intersects with the Fermi-Dirac line, and it's closer to the valence energy. And we pretty much calculate the number of holes by taking the distance between the Fermi and the intrinsic again. It's just now it's lower. And their number of holes is greater than the number of electrons, and the Fermi energy is less than the intrinsic value, and the holes are the majority carrier, and the electrons are the minority carrier. So, that being said, I am going to do an extrinsic semiconductor example, and I'm going to roll up my sleeves even because it involves like actual writing. So we have a material, it's silicon because the band gap energy is 1.12 electron volts. I'm going to change slides in a second. And we're going to find the Fermi energy, which is above the valence band by a certain amount. So we've got Fermi energy above the valence band by 0.25 electron volts. We are given the band gap energy of 1.12 electron volts, so we know it's silicon because that's the band gap energy for silicon. We've got the two values of NC and NV, and KT over Q, which is the thermal voltage, and T is 300 K, so we don't have to do any temperature adjustment in this particular thing. So what we have to figure out from this is kind of what we have available to us. So we know that the band gap energy is 1.12 electron volts, which means that that's going to be the conduction energy minus the valence energy. That's just the difference between the two. And we also then, if we want to figure out, we actually want to figure out what? The number of electrons and holes. Okay, good. So we know that the Fermi energy is equal to the valence energy plus 0.25 electron volts. And that means EF minus EV is 0.25 electron volts. Good. We can also figure out the distance between there and the conduction energy if we want, or the conduction band, because EF, and this is this might help if I move and give you a graphic. So EF is going to be equal to EC minus 0.87. That's the difference between 0.25 electron volts and 1.12. So that's the rest of the distance basically put into that picture. So that means that EC minus EF equals 0.87. And once we've figured that out, the rest of the problem is just purely academic. We can figure out the number of electrons by taking NC and the exponential of minus EC minus EF over, I'm just going to put the temperature there because we know that that's what it's going to be. And we'll get 2.8 times 10 to the 19. I cannot make that look more like a 2. Oh well, it just doesn't look like a 2. Does it look enough like a 2 for you? Okay. I really have terrible handwriting. If I make it like that and put the decimal there, that makes me a little happier. Okay, and then we get the exponential of minus, and we've got EC minus EF, which is 0.87 over 0.0259, and we end up with 7.23 times 10 to the 4 per cubic centimeter. Not so many electrons, but we expect that because the Fermi level is way down close to the valence band. So you should have a small number of electrons and more holes than electrons. So that is not an unexpected value. The value for holes, we take NV and take the exponential of minus EF minus EV over 0.0259. And NV was 1.04 times 10 to the 19. And we use the exponential function and take minus 0.25 over 0.0259. My brackets look awful. There we go. And we get 6.68 times 10 to the 14 per cubic centimeter, which is pretty much what you would expect. Is this N or P-type material?
P-type.
Yes, you should know, and by this point, by either the fact that the number of holes is more than the number of electrons, or the Fermi energy is near the valence band, that it's P-type material. And that should become automatic. You should be able to tell whether it's N or P-type pretty easily, because you've got lots and lots of clues. So we can, and we did this in the participation problem already. We actually used the fact that when you are at thermal equilibrium, you can take the number of electrons times the number of holes, and that's the intrinsic number squared, and you can find that value by taking the NCNV value times the exponential of the band gap, the negative band gap over KT. And we did, that was like one of the last problems that we did. So that's actually a fundamental semiconductor relationship. All right, I'm going to keep going. This is a fundamental semiconductor equation. This just tells us at thermal equilibrium that anytime you know one of the carrier values, you can find the other using the intrinsic number squared. That's basically, you can do that. You can also find the values of the intrinsic number squared by just taking this NCND and take the exponential over EGKT. And somebody already did that, as I said, for 300K. So we can look up the intrinsic values in a table at 300K for silicon or germanium or gallium arsenide, because somebody actually already did that. So if we want to find the whole concentration in silicon at 300K, and we know the electron concentration, we can find the value of the holes really, really, really easily and really, really quickly. And this is something that you should be doing all the time. You should always use the simplest method you can use to find carrier concentrations. So if you know, because there is going to come a time when you're going to have to use something stupidly complicated to find one of them. When we start talking about materials that have more than one type of carrier, that have like acceptors and donors together, there's actually kind of a really complicated equation you use to find the number of one of the carriers. And then the other one, you could use the stupidly complicated equation again, or you could use the one I'm about to use, which is much simpler, and you should always do that. Or you can do both and see if you come up with the same number. Anyway, the whole concentration is just going to be the intrinsic value squared over the electron concentration. So this should become to you second nature for finding the one that you don't know, once you know one of them. So you have to know one of the concentrations in order to find the value, and here we get 2.25 times 10 to the 4 per cubic centimeter for that value. Last time, I think it was, I talked about ionization energy and how much ionization energy it takes for different things to give either an electron or accepting an electron. And that information for you is, well, not completely useless. It's not useless, but it is most of the time not considered when we deal with semiconductors, because when we add donors and or acceptors, because we sometimes can add both, donors donate electrons to the conduction band and acceptors accept electrons from the valence band. But the ability for them to do that, because this makes them ionize, that's what it does. If you're giving up an electron, you're becoming positively charged. If you're gaining an electron, you're becoming negatively charged, so they all become ions. And depending on the temperature, this is really what determines the ability of the dopants to be able to do this process. So at 0 K, and this is one of those things I've repeated a bunch of times, and I think there's at least one conceptual question related to this particular statement, because I say it a lot, but at 0 K, there are no electrons in the conduction band because there's no energy. We call this condition freeze out, because basically everything is just at its lowest energy level and it's not going anywhere. At 300 K, which is pretty much a little more than room temperature, everything has become ionized that could possibly be ionized in the material. So that's something we call complete ionization. In between there, there's something called partial ionization between 0 and 300. However, in here, in this class, we will pretty much always assume that everything has been ionized, because calculations can get really nasty when you start trying to figure out how much is ionized and how much isn't of the donors and acceptors that have been added. So we will generally just assume that if you add donors, all of those donors are going to donate electrons. If you add acceptors, all of those acceptors are going to accept electrons and create holes. So as long as we stay in that range of ionization, we're okay. So I guess the rest of, let me just make sure, yeah, now I get into the messy stuff, but that's okay. You'll be fine. There are other kinds of extrinsic material other than just simply doped with donors or acceptors. If you take an amount of donors and you dope a material and you make N-type material, usually, not always, but usually it's of a level of doping so that the Fermi level is kind of up near the conduction band, and that's that. But you can add a bunch more, and you can create something known as degenerate semiconductors. And degenerate semiconductors are materials to which so much either acceptor or donor atoms have been added that it basically pushes the Fermi energy in the case of N material all the way up into the conduction band, or with P material all the way down into the valence band, which means there's just tons and tons and tons of electrons or holes, depending. And sometimes this type of material is used. There are some particular types of materials that require really, really high doping areas. Even in bipolar junction transistors, you basically have different levels of doping depending on what area you're using. So that could be N material, P material, N material, but they're all doped differently. So sometimes this is required to just create semiconductor material that has a lot of impurities. So degenerate semiconductors is something that you should remember. You should remember this picture. just to know where the Fermi energy is and remember what that is, because that's one of those things that sometimes comes up conceptually. We don't really do any calculations with degenerate semiconductors. We just say this is what one is, and that's what it is. The other kind that I'm going to talk about is a little bit more complicated, and they are what we call compensated semiconductors. Compensated semiconductors basically have both donors and acceptors added to them. So they can actually have, if you've got, say, silicon, you can add boron and phosphorus. So you're adding extra electrons and you're adding extra holes. And that can come up with some kind of weird stuff when that happens. So basically, when we have compensated semiconductors, we add acceptors to N-type material or donors to P-type material. Then we can still classify it. If the number of donors is greater than the number of acceptors, we call that N-type compensated semiconductor material. And if the acceptors are greater than donors, that's P-type compensated semiconductor material. And then if they're equal, it's completely compensated. And I don't know if I've really ever come across that. If you have conditions where everything's ionized, and I already said that it was, then the acceptors that are added plus the number of electrons is going to equal the holes plus the number of donors. So we can use the fact that we have thermal equilibrium holes and electrons, and I'm going to do I'm not going to do too much math, actually. I'm just going to tell you where this comes from. I'm not actually going to solve this, but you will have to use it. We can look at the fact, yes, oh, I forgot, I didn't show you that. I just said it, I didn't actually show it to you. Anyway, we can use that fact, and we can actually create an equation where we're using the balance of the electrons and holes, and we can say that the number of electrons in the material plus the number of acceptors is equal to the intrinsic number squared over the number of electrons plus the number of donors. And this means that we can create for ourselves a quadratic equation. And for a quadratic equation, since we want to find, say, the number of electrons, we just have to get the solution, and I'm just going to tell you what it is. I'm not going to go through it, but that is what the solution is. So I want to stop for a second and actually look at this equation. First of all, if the number of donors is several orders of magnitude or even a couple orders of magnitude greater than the number of acceptors, if you subtract an order of magnitude less number from a number, you're basically just going to get the original number. If you have 1 times 10 to the 16 and you subtract 1 times 10 to the 14, you still have pretty much 1 times 10 to the 16. So if the number of donors is much greater than the number of acceptors, and this value is not too close to the number of donors and acceptors, then you can actually kind of estimate the values. So, in other words, I just got to write in a weird place, but if the number of donors is much greater than the number of acceptors, like a couple of orders of magnitude, oops, go backwards. Stop, don't do that. And if Ni is reasonably less than the number of donors, then you can say that the number of electrons is just equal to the number of donors. So you don't always have to do this whole messy thing. You have to kind of use what you know about numbers to figure out if you really have to do this or not. So in the case of, say, silicon, if you had donors that were 10 to the 16, you had acceptors that were 10 to the 13, and you know that the intrinsic number is like 1.5 times 10 to the 10, the number of electrons is going to equal the number of donors. Even if you go through this whole process and do this whole equation thing, you're going to come back with what you started with. But If that isn't the case, then you definitely have to go through and do this. And actually, if the number of donors and acceptors is even, like if you had, say, 5 times 10 to the 16 donors and you had 2 times 10 to the 16 acceptors, you could just subtract them, considering that the NI is like really small. Can't always do that, but that's okay. So this is basically the equation that comes out for both electrons and holes. You don't need to use both of them, though. You can. They both work. So if you have a number of donors and number of acceptors, if you want to figure out the number of electrons and the number of holes in one thing using both long equations, you can. But general, it's better to use one and then just find the other value using ni squared over whatever, because that's going to be much easier. Or you can check your answer by doing that, because you should come out with the same thing. Let's see. So, yes, well, I'm going to switch slides for a second, but it's going to have the same thing almost on it, but it's going to say what I already said, because this is what happens when I talk and I forget that I have stuff written down. So, this is what I just said in a different form.
So the double arrows, is that just being greater than?
Much greater than. Yeah, that's the standard definition of double arrows, means much greater than or much less than. There is no standard definition for what much means, but usually it's much, like a lot. So, all of this stuff, and this is kind of changing gears. Do you have a question?
Just real quick.
Yeah.
For the much greater, do we have to know exactly based on the problem, or what you tell us in the problem?
You would have to know, but if you're ever unsure, just go ahead and use the long equation. And then if you come out with what you started with, you'll know it was much greater. So it's kind of a judgment call, and that's one of the weird things about being an engineer, is that you actually have to kind of think about things logically and think about what you would expect based on what you're given number-wise. But you can just kind of have to think about it. And if you're worried about it, just use the whole equation and you'll be fine. Temperature makes a big, big, big difference in how many carriers you get. And you've seen that. You've seen the number of carriers goes up as the temperature goes up. And it's a very strong function of temperature because it's an exponential. So we actually have temperature in an exponential that's dealing with the carrier concentration. That's going to be really large. So what happens is when the temperature goes up and up and up, that value of ni squared gets bigger and bigger and bigger. And if it gets big enough, it overrides the acceptors and donors that have been added. And what you actually end up with is intrinsic material again, if the temperature gets too high. So what this looks like graphically, this is just sort of a graphic of what this would be. The areas that would be partial ionization, which is the area we don't talk about in here, that evil area in which everything's not ionized. And then there's a long area in which we have extrinsic material, which has stable donor amounts. The donor amount is like 5 times 10 to the 14, and that means the number of electrons is about 5 times 10 to the 14, from 100 up to about 500K. And you notice that the intrinsic carriers start out really low and start to increase as temperature goes up. And you notice there's a point at which those two curves meet. And that means that we no longer have extrinsic material at a high temperature. So that changes radically the electrical characteristics of the semiconductor. So that's one of the reasons we have problems when they get too hot. Now, 700K or even 600 is really, really hot, but that can certainly happen depending on what application you're using. So I'm going to do an example with compensated carriers because sometimes these are a little bit confusing. They're not terrible. So we have donors and acceptors, and you'll notice that they're kind of, sort of in the range, and this is silicon. So I could almost, but not quite, just subtract. Actually, in looking at this, I'm going to prove to you that I can just subtract. The number of acceptors is 2 times 10 to the 16. The number of donors is 5 times 10 to the 15, and that's the same as 0.5 times 10 to the 16, which means, since I know that Ni is like 1.5 times 10 to the 10, I am expecting that the number of holes, because there are more holes than electrons, that the number of holes is going to be Na minus Nd, which would be 1.5 times 10 to the 16. That's my guess. And then I'm going to do the long equation just to do it, to see if I get the same number. And if I do that, if I do the long equation, I take Na over Nd over 2, and then I add the square root. Ooh, that's a terrible square root. That's like the worst square root I've ever made. So I'm just going to make that go away and make a better one. All right. There, that looks better. So then I take Na minus Nd again over 2, and I square it, and I add Ni squared. So I know Na minus Nd is 1.5 times 10 to the 16 over 2, and then I add 1.5 times 10 to the 16 over 2 squared, and this is actually all over 2, plus 1.5 times 10 to the 10 squared. And indeed, that does end up being 1.5 times 10 to the 16 per cubic centimeter. And that's because the acceptors and donors are many orders of magnitude greater than the intrinsic values. So when that happens, you can basically just subtract one from the other, and you'll be fine. You just have to make sure that you take the larger one and subtract the smaller one from it. That's really the only caveat. So you can find the number of electrons by taking the intrinsic number and dividing by the number of holes. So we have 1.5 times 10 to the 10 squared over 1.5 times 10 to the 16. And we get something really, really small, I think. Yes. 1.5 times 10 to the 4 per cubic centimeter. And if you went through and did this in the long equation, you would get the same answer. You would take donors minus acceptors, and it would end up being a negative number, so it would subtract from that square root number. You'll end up with the same number, but it's really easy to make a mistake when you do that. So it's best to just use the short version to get the final answer. Let's see. Yes. Last thing I'm going to do. Yes.
Where did we get the Ni from? Is that from the P-type silicon?
No, that is actually from a table. Somebody sat down, some scientist, and found out how many expected value of electrons we have in intrinsic material. So there is a table that gives you those values.
It's a constant.
Yes, it's a constant. Although I had a student who was told that it was 1 times 10 to the 10, and I guess he was at a different school, and it was, and he was like, "Why is it different?" I'm like, "Well, that's not that different. I mean, 1 and 1.5 times 10 to the 10 is not a huge difference, but I guess it was because the school wanted to make it simpler. I don't know." Okay, last thing I'm going to talk about is, again, and I harp on this a lot, is the Fermi level and where it is. We've used the Fermi level to find N material, P material, and all that. And we've used the difference between the levels to find the number of electrons and the number of holes. So we actually can find the difference between either the conduction level and the Fermi level, so basically how far below the conduction band the Fermi level is, and we can find how far above the intrinsic level the Fermi level is for N material. And that's basically just a rearranging of equations that you've already seen. We get the same thing for p-type. The only thing that's different is now I changed slides, just so you know. This is like a different slide than I had a second ago, if you're writing it down. So I had that one, and then I went to this one. So I don't want you to be writing one equation, then you get another one. But, so yes, we use pretty much, so basically what this means is that I can tell you that there's a number of carriers and a temperature and a material. And you should be able to tell me how far below the conduction energy the Fermi level is, or how far above the intrinsic level the Fermi level is, depending on which equation you use. And this is the one for P material. It's really similar. It's almost exactly the same. But I'm going to do one more example. This is the last example. And this talks about the Fermi level, and it's a little bit complicated, but it's a good problem. So we have silicon at 300K. We have everything at 300K pretty much. I think the homework for this week has one temperature dependent, or not for this week, for this section, has one or two temperature dependent problems, and then everything's just at 300K, because pretty much that makes it easier. And that's really where we live anyway, so we want to talk about where we live. So we have acceptors of 10 to the 16, and we want to find out how many donor atoms we need to add so we can make this p-type material into n-type material, and we can move the Fermi energy so it's 0.2 electron volts below the conduction band. So, how would we even approach that? Well, we have to kind of work our way backwards. So, first of all, we know that the number of electrons we need is going to be using this equation, which we've used before, that uses the difference between the conduction and the Fermi energy over KT, and since we're at 300K, I'm just going to use the electron volt value. So we can figure out the number of electrons that we need, and then we also know that because this will be compensated material, the actual number of electrons here, I'm just going to put this up here, is going to be how many we add minus how many we had. So the donors minus acceptors is going to equal the number of electrons pretty much. So first of all, we can use the NC value, which is a constant from a table, and take the exponential of minus 0.2 over 0.0259, and we end up with 1.24 times 10 to the 16 per cubic centimeter. So in order to get the Fermi level where we want it, that's how many electrons we have to have. So that's how we got to that point. That means that the number of donors minus the number of acceptors is going to equal 1.24 times 10 to the 16. And that, whoa, I don't know what that is. Gosh, go away. That means the number of donors we need to add is the number of acceptors plus 1.24 times 10 to the 16, which is 1 times 10 to the 16 plus 1.24 times 10 to the 16, which is 2.24 times 10 to the 16 per cubic centimeter. So that's how much we would have to add to create N-type compensated material that would have a Fermi level at that point. Most of the time, no, I'm not going to say that. No, I was going to say it, and I'm not going to say it. So just forget it. Sometimes I say things, and then I take them back. It's better if I just say it and think, and then don't have to. So you don't know what was in my head, and you'll never know, because I'm not going to tell you. That is all we need to talk about with, this is basically, I think I finished chapter 4. I believe. I think that's the end of chapter 4. And chapters 5 and 6 are not as complicated as 4. Chapter 5 covers current and how we get current, and then chapter 6 covers non-equilibrium conditions, of which we don't talk about much. There will be a homework posted for this section of these 3 chapters, which I should have done by the end of the week. It's almost finished. So I think there's a couple problems on there that we haven't gotten to yet, but you can open it and do it and then, finish it when we get to that point.